I'd now like to welcome to the stage Noah Helman from iMicrobes.
Hi, good morning, everybody. Usually my walk-up song is Led Zeppelin, but that'll be okay. Yeah, next year, right, exactly. So thanks to everybody, Paul and the team for inviting us today. My name is Noah Helman. I'm one of the three founders and CEO of Industrial Microbes. We're working on carbon-negative chemicals and materials for a circular economy, and actually it's a really good fit for what we've heard from a bunch of companies this morning, Matt from DMC and Niels from Chaincraft as well. There's sort of three C's that I think are important. There's the carbon impact, the circularity, but also the cost competitiveness. And so I'll try to address all of those today. So I don't need to, as we just heard, we don't need to talk to you about circularity and remaking the economy. The world around us, all these materials and chemicals, something like 95% of manufactured chemicals are touched by manufactured materials are touched by the chemicals industry. And as you know, 6% of global emissions come from chemicals and materials broadly. So we need to rethink how we're doing that. In addition, we have waste filling up landfills. The products that we use are so disposable because they're so cheap. We need to find a way to get around this idea of the linear economy and move to a more circular process. Everybody knows we want products to be made better for the future generations. So what I'd like to invite you to do is imagine, what does that actually look like? What does an ideal circular economy look like for us? We want the same products. We want the same quality of life. We have this waste stream. To make a circular economy, we need technologies that can take that waste and repurpose that as the raw materials to make all the chemicals and materials that we use today. We see that the next generation feedstocks that should be used have to come from that waste, and in particular we focus on things that are C1 molecules like methane and methanol that we can get from organic sources similar to what Chaincraft is talking about as well. We focus on methane because it's 86 times worse for global warming compared to CO2, and the International Energy Agency estimates that something like 700 million metric tons per year of biomethane could be generated. We cannot allow that into the atmosphere, obviously, and the way that we can stop that is to create some value from that. Right now, what we do with methane is we burn it for heat and electricity, and we're not going to need to do that anymore. The energy transition is going to provide low-cost, renewable electricity and heat. And so we need to find something else to do with that methane that creates more value from that. So what we're working on is building the world's most programmable methane-consuming microorganism from which we can make chemicals, okay? And we've done that recently with the effort over several years to make E. coli bacteria that can consume methane as a feedstock. That's very different from most of what people typically do. I think there have been a bunch of companies talking about doing fermentation. Usually we're talking about using sugars or other substrates, but we can consume methane and prevent it from going into the atmosphere, turn it into chemicals, and create real value from that. Now, the real trick in doing this was to figure out a way to turn methane into methanol. That's the first step in this process. I was speaking to somebody yesterday here who said, oh, turning methane into methanol at standard temperature and pressure, that's like a holy grail of the chemical industry, and I should have offered him a job right there on the spot. So actually, it's amazing that biology has been able to do this, right? There are microorganisms that live in the bottoms of swamps that can turn methane into all the molecules that they need to survive. But they're not really suitable for chemical production. Companies have tried that, it didn't really work. So what we did was we took that enzyme, put that into E. coli, used a synthetic biology approach to wire that up and connect that to metabolic pathways. When we started this process several years ago, we called up one of the world experts in this field and said, we want to turn E. coli into a methane-consuming bacterium to make chemicals. And she literally laughed at us. She was like, find a different problem. I've had so many grad students and postdocs try to do something similar. That's a giant waste of time. But actually, a few months later, my co-founder and CTO, Liz Clark, figured out a way to do it. We were just barely seeing any activity, and over the course of several years, we have now engineered that system to be operating at rates that are commercially relevant. So we've built a techno-economic model that tells us how fast does this system need to work in order to be cost competitive, and we have now achieved and exceeded those rates for the products that we're looking at. As a result, we've been issued more than 20 patents in the US, here in Europe, in Asia, and we're moving forwards with these pathways. We've actually applied the technology to several different metabolic pathways for different products. We've sent out samples to industrial partners. The purity has always exceeded their expectations, and we're moving forward in partnership with them towards commercialization. Our initial products are things like acrylic acid, which is used in paints and coatings, diapers, and personal care. Methacrylates, which are used for things like plastic glass, like plexiglass and lucite. And acrylonitrile, we heard about earlier today as well, has applications in things like carbon fiber, synthetic rubbers, and hard plastics, and other products in development. In fact, I have a sample right here. If you come talk to me afterwards, I'll tell you exactly what that is. So, the third C, besides carbon negative and circular, is that we need to be cost competitive. And so this is a really important driver. Matt was talking earlier today about needing to be able to achieve scale, and scale is driven by being cost competitive, or even better, having a cost advantage. So this is a really critical aspect to this. We have built a techno-economic model with the help of 2 experienced bioprocess engineers that have actually designed and built and implemented large-scale fermentation facilities. And as a result, what we calculated from that model was that we could achieve bio-based acrylic acid production at half the cost of what it is being made for today. And if you're interested in exactly how we do the calculations and how we figure out what the carbon footprint is, you can go to our website, iMicrobes.com, and download this white paper with a bunch of the details, or come talk to me afterwards. Derek and Liz and I have worked together for more than a dozen years. We were at a different company together for about 5 years. We saw all of the problems that the industry had in that early set of troubles where folks raised too much money, put steel in the ground, and then didn't manage to make any money from that. And what we learned there is to be pragmatic about things like techno-economics and make sure that we can be cost competitive. So all the products that are around us today, we can make those a different way. We need to find a way to do that. We'd love to partner with folks in this room to figure out a way to take your chemicals and materials and make them a different way that's carbon neutral, so we can partner together. Typically, we work in partnership with large companies where we develop strain and bioprocess and work together to scale that up, and then eventually our partners will commercialize that through their existing sales channels. So please get in touch. My email is here, noah@iMicrobes.com. You can go to our website and download this white paper, or come find me afterwards. Happy to share a fermented or distilled beverage with you later today. Thank you very much.